When we start studying alternating current, we're going to need a review of complex numbers because we're going to run into some complex impedances, and we'll talk in more detail about that later. But let's set some mathematical groundwork. So suppose we have a point here. This point has an x and a y coordinate, and my y-plane is actually the complex axis, and my x-plane is the real axis. So that means that any x kind of part of my coordinate is going to be real, a real number, and any y part of my coordinate is going to be a complex number. So then if I use my trig skills that we reviewed in the last video, if I turn this into a triangle, then this is my y length, this is my x length, and this is the radius of my unit circle if I were to write this all the way around for all angles here. So then this means that the y part of this number is going to be the complex part of the number, and the x part of the number is going to be the real part. Okay, so then if we put this together, the complex number will consist of a real part and a complex part, or an imaginary part. So it's denoted z is the sum of these two parts, I times y, okay? Where this is the real part and this is the complex part. But we're electrical engineers, and so we use I for current. So instead of using I, we're going to replace the I with a J. Okay, so our complex numbers are going to be in the form x plus jy. Okay, so then in the last video when we reviewed our trig functions, we saw that this x here can be written as r cosine phi, and y can be written as r sine theta, because these arguments might not necessarily be the same. So then if I replace the x and the y in sinusoidal form, then I can write my complex number as r cosine phi plus jr sine theta. Okay, so then at this point, recall Euler's identity that says that we can express this in exponential form by this relationship. E to the plus or minus j phi is equal to cosine phi plus or minus j sine phi. Okay, great. So now we get to use Euler's to write this in exponential form. So if I want to write this complex number in exponential form, it looks like this. That same z from before, so this is just called rectangular form, can be written in exponential form as r e to the plus or minus j phi. Okay, great. So then what we get to do is, since we can define r as basically the hypotenuse of that triangle, I'll say since r is equal to the square root of x squared plus y squared, then I can express this same z as z is r at an angle of phi, and this is called polar form. Okay, so we're just learning how to go back and forth between all these forms. So this is polar form. Our original form was x plus jy. This is called rectangular form. And then exponential form was z is equal to re to the j phi. This is exponential form. And then the last form we have is sinusoidal form, and this is r cosine phi plus j sine theta, and this is sinusoidal form. Okay, so we're going to have to know how to go back and forth between all of these forms, because sometimes we will be given problems in this form and we have to express it in either polar or exponential or sinusoidal form. So this is beneficial if we are given our voltage or our current signals in sinusoidal form, and these forms are going to be pretty useful when we start talking about complex impedances, which we'll get to later. So let me know if you have any questions about the complex number review.